we're talking about, we just finished talking about R, and then we were talking about C, the complex numbers. Basically, this is being introduced as an example of the kind of space that we'll be working in. Okay, this is a course, I know that this course is often called real analysis. That's a misnomer. This is not a course in real analysis, it's a course in analysis. Okay? And so the spaces that we're going to be working in it's not the real numbers, it's so-called metric spaces. Okay. So metric spaces, we haven't even defined those yet, but the real line is an example of a metric space, but so are the complex numbers, so is Euclidean space. And so we're going to talk about the complex numbers in Euclidean space. Oddly, the course that was called Real Analysis when I was in school is what they call here graduate real analysis, measure theory, measure and integral. So that's what when I say real analysis, that's what I mean. This is sort of like the foundations of analysis. Yeah, that's what we're going to get across to you all, the foundations of analysis. Okay, so, so the complex numbers, we started talking about them. Basically just some basic properties of continuing with complex numbers. So just like how the real numbers have an absolute value, complex numbers also have an absolute value. So if you have some point in the complex numbers, then the absolute value of z, also called, I don't know why it's called this, but people often use the term modulus. The modulus of z, usually denoted like the absolute value, is defined to be the square root of the product of the number against its modulus. Okay, remember that the complex function, so if z is a plus bi, then z bar is a minus bi, right? And so z bar is just going to be a squared plus b squared. So it corresponds to your normal Euclidean notion, right? If we're thinking about this as a and bi in the plane, then it's just the distance to the origin. And luckily we proved that such numbers do exist in the real numbers, so we don't have to worry that those numbers exist. Right. So this is okay. So then we have some basic properties of the absolute value. Actually, my brother broke his nose last weekend. That was not this week. Sorry to be precise. Properties of the absolute value. It's bigger than 0 for all z not 0. And of course is 0 equals 0 if z is 0. Z is the as you might expect, the modulus of the complex conjugate is the same thing as the modulus of the original. The modulus of the product is the same thing as the product of the moduli. The real part is, of course, smaller than so the absolute value of the real part is less than or equal to the absolute value of the point. And last, the complex absolute value also satisfies a triangle equality. Okay. Okay, the first two are pretty straightforward. The third one kind of has a cute proof, which is that you say, well, proof of C, observe that if I take this thing squared, that's the same thing as right. So like the square, of course, the square of the modulus is just the product of the point against its conjugate, right? So this is just this guy against its conjugate, right? But we saw, as we mentioned last time, the conjugate of a product is the same thing as the product of the conjugates, right? And you can, of course, reorder this. You can reorder this and then see that you get the square, the product of the squares of the moduli. Okay, so what does that tell you? That tells you that that both of these things, so that this and this are square roots of the same number, the same real number, right? In fact, they are positive, assuming that both of these things are non-zero. Otherwise, it's easy, right? But then they're positive square roots of the same number, and when we proved that theorem about square roots, we said that the square roots are unique, right? So that tells you that they're equal. Okay, so that's kind of a cute way of showing the equality of that the modulus of the product is the product of the moduli. The fact that the real part is smaller than this, we can maybe the easiest way is to I don't know I forget if I mentioned this before or not, but one kind of useful trick. When you're dealing with for A and B greater than or equal to 0, when you're dealing with non-negative numbers, then A being less than B is equivalent to A squared being less than B squared. Right? If A is less than B, then certainly A squared is less than B squared. And vice versa. If A squared is less than B squared, then A is less than B. Right? This is because the square function, right, is a strictly increasing function. Right? So if A is less than B, then A squared is less than B squared. And similarly, if A squared is less than B squared, then going backwards, A is less than B. Okay. So one useful trick for proving inequalities is that sometimes you're trying to prove something, and then it's just useful to look at the squares. If you can prove it for the squares, then you've got it for the original, right? So right. So it suffices to show that right. So it suffices to show that the square of this guy is less than or equal to the square of that guy. right? But the square of this guy is a squared plus b squared. Right? Assuming that z is a plus bi. Right? The square of this guy is a squared plus b squared. The square of this guy is a squared. Right? Certainly a squared is less than or equal to a squared plus b squared. So we're done. Okay, everybody okay? Any questions? It's not the most exciting thing. Today's lecture, nothing too amazing. Okay, so yes, Sandy.
For the a squared, would that be equal to the real value of z squared?
Oh, I'm sorry, yes. Yes, thank you. Okay, so then let me prove this last one. Okay, so proof of E, same sort of thing. So we want to show that this is less than or equal to this. Right? We'll just square both sides because again we're dealing with non-negative numbers. Okay, and again nothing too fancy. Z plus W modulus squared. Well, that's going to be z plus w against z bar plus w bar. Right? Well, so that's going to be z bar plus w z bar plus z w bar plus w bar. Just distribute the property. So that is to say z bar plus, z modulus of z squared plus modulus of w squared plus this guy here, right? So this is w z bar plus z w bar. Can anybody say anything interesting about this? What's w z bar, z w bar? What's the relation between these two guys? Is there any relationship? Sure there is, right? This is, let me read it this way, z bar w, this is z w bar. So one is the conjugate of the other, right? Right. Z bar w bar over both of them is going to be z bar w bar, which is z w bar, right? Right. So you're taking something and summing it with its complex conjugate. What happens when you do that? You get twice the real part. Right? So you get twice the real part of one of them. Right? You get twice the real part. And what we just said was that the size of the real part is smaller than the size of the thing itself. Right? So we invoke that. We get that this is less than or equal to this plus twice the size of this. Plus this. Right? And you recognize that to be just z plus the root quantity squared. Okay, so the triangle inequality is true for complex numbers. Any questions? Anybody okay with that? It's just a calculation. Okay. Another property or another inequality that that will show up over and over again is the so-called Cauchy-Schwarz inequality. Okay, so this can be written like this. Suppose you have complex numbers, a1 to an, and b1 to bn. Okay. Really what you have is a complex vector, so maybe I should write it that way. So you have a1 to an in Cn, b1 to bn in Cn also. Okay, so you've got vectors where the components are complex numbers. Okay. Right. Then summation of the dot product, well, the inner product of one vector against the other. If you look at the size of that, then that's controlled by the norm of one times the norm of the other. Okay, so, right, I can say that this is analogous to the real case, right? In Rn, right, in Euclidean space, right, you have two vectors, a1 through an, and b1 through bn. And then you take the dot product, right? So you take, A dot B, and that's controlled by the magnitude of one vector times the magnitude of the other vector. Right, that's a Cauchy-Schwarz inequality. And that's exactly the same thing here. Exactly, literally. Okay. So, I think. Yeah, so I'm not going to prove this. I'm not going to prove this in a complex case. I'm going to quickly introduce the Euclidean. Introduce the Euclidean space, and then prove it in the Euclidean case. The reason is that it's basically the same proof, but just the way that it's written in the text is kind of obfuscated. So I'm going to write it in this case, and hopefully you can see, if you look at it, you can see that it's exactly the same proof. Okay, so has everybody seen Euclidean space before? It's just like n vectors and this sort of thing. Everybody okay with that? Close your eyes for a second. Raise the hand if you have not seen Euclidean space before. Okay, put your hands down. Okay, so I'm gonna sort of quickly. A couple people haven't, or maybe a little bit shaky. So let me just review Euclidean space. It just means you're taking n copies of the real line. You're taking a plane. You're taking space. You're taking four-dimensional space, whatever. Right, so Rn is just vectors, x1 and xn, where each of the xi is a real number. Okay. It's a product. It's a product of n copies of the real line, right? Just like the plane is a copy of the real line crossed against the against the real line, and so on and so forth. A what's called a Cartesian product, right? And as you're probably well aware, you can add things, right? So if I have x plus y, we can define an addition on the space, which is simply component-wise addition: x1 plus y1, x2 plus y2, xn plus yn. Right. So there's a way of defining an addition. There's a way of defining scalar multiplication. So if you have a number in the reals, and you have a vector in Rn, then you can define the scaled vector, right, just by scaling every component, right? So you have alpha x1, alpha x2, dot dot dot, alpha xn, right? So it just means that you've stretched every component by that factor. You've changed the norm. You've multiplied the norm by alpha. Okay. So this is like the basic operations, vector space operations. You have the inner product, the dot product, of course. X dot y is summation xi yi from I equals 1 to n. You have the norm or magnitude, right? The magnitude of the vector is just the dot product of it against itself, and then you take the square root. And that's it. Okay, so right, it's just you've got the space, you've got some algebraic properties, and you've got some notion of size. Okay, you've got some notion of size. The notion of size leads to a definition of distance, right? The distance between x and y is going to be the magnitude of the difference. The magnitude of the difference, just like in the line, on the line, right? The distance between 2 points, A and B, is the magnitude of the absolute value of the magnitude. I'm sorry, the magnitude of the absolute value of the difference. Sorry. Yeah. Okay, so it's just an extension of that. Okay, so it's a vector space and it's a norm, and the norm satisfies certain properties. Namely, as before, the norm of the vector is greater than or equal to 0, and is 0 if and only if x is the 0 vector. If you scale a vector and then take the norm, you get the absolute value of the scalar times the norm of the original vector. There's a Cauchy-Schwarz inequality. The norm of the dot product, the size of the dot product is controlled by the product of the norms. There's a triangle inequality. Right, the norm of the sum is controlled by the sum of the norms. Okay, and the proof of the triangle inequality, we can get that in basically the same way. So you say, okay, so proof of the triangle inequality. If we look again at the square, then that's going to be x plus y dotted against x plus y. You can kind of see what's going to happen, right? Same sort of thing's going to happen. You're going to get x dot x plus 2x dot y. plus y dot y. So it's not exactly the same thing because we don't have that complex conjugate going on, right? Right. The inner product is, yeah, it commutes. Right. But we can see that that is less than or equal to, this term is exactly the norm squared. This term is, again, exactly the norm squared, right? This term in the middle we can control by the product of the norms, right? By the Cauchy-Schwarz inequality, right? X dot y is certainly in magnitude less than the product of the norms, right, by the Cauchy-Schwarz inequality. So we put that in, and then we've got it. Basically the same proof, except we have to use the Cauchy-Schwarz inequality to get this control of the cross terms. Okay, so that's just algebra. But I should say that in analysis, the triangle inequality shows up everywhere, right? So analysis is sort of like a lot of analysis is trying to understand things by controlling their sizes. When I was in grad school, one of my professors made the following joke, which I found completely unfunny at the time. But he said, somebody asked me, what's the difference between algebra and analysis? And I said, in algebra, they use the equal sign. In analysis, we use the less than equal sign. Is it funny? Anyway, I find it kind of funny now, but anyway. Okay. Yeah, but triangle inequality shows up everywhere. Everywhere. Okay. So what should we do now? Let's prove the Cauchy-Schwarz inequality. So Cauchy-Schwarz inequality. Okay. So remember, let me remind you of this notation. So A, B, then if we have like the unit ball here, then this vector is, of course, the normalized vector, B divided by its norm, right? So that's its direction, right? And remember that this thing here can be written as A dot B over the magnitude of B times that direction. Okay, so this is the so-called, this thing here is sometimes called the scalar projection. Scalar projection of A on B. And then the whole thing itself is called the projection, or the vector projection of A on B, denoted by proj A, B. Okay. So one way you can think of this is that you're decomposing your vector into two vectors, one of which is parallel to B and one of which is perpendicular to B. Okay, so you've got this parallel part and then the perpendicular part. This part here is, of course, A minus the parallel part. Right. Okay. So we want to show that the dot product of A against B is controlled by the product of the norms. Okay, and that turns out to have the following geometric meaning, that this thing is bigger than, the magnitude of this is bigger than 0. Okay, that's it. So Cauchy-Schwarz inequality is equivalent to the statement that the magnitude of this thing is bigger than or equal to 0. Okay, so let's see that. So let x denote this number a dot b over magnitude of b squared. Okay. So we know that 0 is less than or equal to this guy squared. Right? That's our statement, that a minus projection is greater than or equal to 0. A minus its squared is greater than or equal to 0. Okay, and we just calculate it out and see what it means. So this is going to be a minus xb dot a minus xb. Okay. That is a squared, I'm sorry, a dot a minus 2x a dot b plus x squared b dot b. Okay, so right. Well, what's that? Let's just write it out. We get magnitude of a squared minus 2x a dot b over magnitude of b squared plus x squared. So that's a dot b quantity squared over magnitude of b to the 4th power times b dot b, which is the magnitude of b squared. Right? And so what is that?
I think you might need an extra a dot b.
Oh, thank you. This one, maybe. Thanks. Thank you. Okay. So, right. So this, we cross up two of those guys. This changes to it. This 4 changes to a 2. Right. We've got minus 2 of these guys and plus 1 of them. So we end up with magnitude of a squared minus just one of these guys, a plus a dot b quantity squared over magnitude of b squared. Okay, so so what happens, right? We end up with 0 is less than or equal to this, right? In other words, a dot b squared over magnitude of b squared is less than or equal to a squared, right? Multiplying both sides through by magnitude of b squared gives us the square of the Cauchy-Schwarz inequality, which gives us the Cauchy-Schwarz inequality. Okay, so I've cheated you. I mean, I've cheated a little bit because I've assumed that B was non-zero. But if the magnitude of B is 0, then the Cauchy-Schwarz inequality is trivial, right? Because that would mean that B is the 0 vector, and certainly A dot the 0 vector is less than or equal to 0. So you don't have to worry about that. Okay, so that's the proof of Cauchy-Schwarz inequality. One of many. I have a book in my office. The whole book is devoted to different proofs of the Cauchy-Schwarz inequality. So, there are other ways of thinking about it, of doing it. It's useful to be able to think of things from different perspectives. I was reading an article by an old professor of mine, and he said, I started writing down some different ways of thinking about the derivative. And he wrote down, in this article, he lists, I think 8 different ways of thinking about the derivative. And then he says, here's number 37 from my list. And he talks about the 37th way he thought about thinking about the derivative. That's actually kind of wise advice. You want to be able to shift your perspective. Okay. Okay, that is pretty much all I want to say about chapter 1. Chapter 2 is called Points at Topology. So historically, this is a field that develops kind of after the kind of the great change of perspective that was created, that was instigated by Weierstrass in the mid 19th century. So this is starting in the early 20th century, where people start to ask, what is actually necessary for these results to hold. And so you have these sort of generalizations of the properties of spaces. So it's like properties of spaces that would cause, the things that were crucial for these phenomena to occur. Okay, so they're kind of extracted from it. So it's kind of an odd. I really like this stuff, but it's like one level of abstraction higher than straightforward analysis, I'd say. Okay, so the first thing we're going to do in this chapter is a notion called countability. Countability, countable, maybe countable and uncountable sets. Okay, so we'll introduce just a bunch of not so interesting definitions to get us up to the definition that we really care about. Okay, so first, you have 2 sets, A and B. You have F, that's a map from A into B. Okay, so this is the kind of notation that I'll always use. F is a map from A into B. So A and B are sets. F, a function, a mapping. Okay, so if E is a subset of A, then we denote F of E to be all the points F of A where A is in E. Okay, so this will be a subset of B. Right, so here's A, here's B. F is a map from A to B. E is some subset, right? And you're looking at all the things that you get when you take the points of E and map them through F, right? So it's like all the outputs. Okay. This is called the image of E under F. Okay, related to that, if F of A covers all of B, we say F is onto, or surjective, if you want to use the French word. The Bourbaki word. And sometimes, if I'm feeling like it, I'll write it like this. So use a double arrow for the surjective map. I think that might also be the Bourbaki notation. Okay. Definition number 3. For E, a subset of B, we write F inverse E is all the points in A that get mapped into E. Okay. So here you've got A, you've got B, and you've got some subset E here now. And you're looking for all the points that get mapped into there, right? The collection of all the points that get mapped into E, those guys are called F inverse E. Okay, so all the points that get mapped over there. Okay, so this is called the inverse image. Yeah, and sort of like a subnotation. If I write F inverse of a single point, what I mean is the inverse image of the set of that single point. Okay, so just it's a little bit pedantic, but yeah, this is F inverse is for a set, right? If I say F inverse of a point, what I really mean is F inverse of the set consisting of that single point. Okay, it's nothing. Okay, definition 5, if for all points in B, the inverse image of that single point is let me use this notation. So for this notation, it means like the number of points. So num equals number of points in a set. Okay. Sometimes you'll write it like this, like number of points in a set A. Sometimes it's written with the absolute value sign. Sometimes people write it like this, card A for cardinality. We haven't defined cardinality yet, so let me get to that in a second. So if the number of points in the inverse image is always less than or equal to 1, then we say that F is 1 to 1. Okay, or injective. A 1-to-1 map or an injective map. Okay. It just means that there's only one point that gets, if it just means that you can't have 2 points that get mapped to the same point, right? You can't have that, right? At most, you've got 1 point in the inverse image of each point. Okay. Not a 2-to-1 map. So equivalently, if x1 and x2 are different, then f of x1 and f of x2 are different, right? You don't have no two different points go to the same point. You've probably seen this term before. And again, one sometimes uses this, this arrow for that. Okay. Okay, so now here's the real definition. Here's the definition that we really care about. If f from A to B is 1 to 1 and onto, then we say that A and B have the same cardinality. That the cardinality of A equals the cardinality of B. Okay. Okay. So just to give you a simple example, like if I take the natural numbers, right, and then I create a map f of n equals 2n, right? Then that map takes me to 2, 4, 6, 8, blah, blah, blah. And so the set of natural numbers has the same, the cardinality of the natural numbers is the same thing as the cardinality of the even numbers, right? Kind of obviously, right? You can create a map you can create a one-to-one onto map from the natural numbers onto the even numbers, and vice versa, of course. Right. Notice that if this map is one-to-one and onto, then the inverse map is also one-to-one and onto, right? Then there is an inverse map which is also one-to-one and onto. So if A has the same cardinality as B, then certainly B has the same cardinality as A. Right. This is a so-called equivalence relation. Right. If A has the same cardinality of B, we also have, if A has the same cardinality as B and B is C, then certainly A has the same cardinality as C. A has the same cardinality as itself. So it's what's called an equivalence relation. So having the same cardinality is an equivalence relation. So cardinality is basically a way of extending the idea of size of a set. So like in your normal plebeian world, you've got the size of a set, right? You've got number of students in the room, it's got some size, right? But now we can talk about the size of an infinite set, right? We can say this infinite set has the same size as this infinite set, okay? We'll also see things that, like this infinite set does not have the same size as this other infinite set. In other words, there are different sizes for infinities, right? So this is something that this theory was developed by Georg Cantor in the like 1870s, I think, something like that. And it caused a terrible uproar, right? Like the mathematicians thought this was an abomination. Many of the things we'll show you were thought of as abominations at the time. Okay. I forget what kind of cruel words were directed at Cantor, but there were plenty of them. Yeah. But later, I think it was Hilbert who said something like, "Nobody shall shake us from the paradise that Cantor has created." Yeah, so ultimately he got his recognition, but by that time I think he was already dead. Yeah. Okay. Okay, some terminology. If we let j sub n denote the natural numbers from 1 to n, 1 if A has the same cardinality, and for the moment I'm going to use this to indicate has the same cardinality. Okay. That will probably change later, but for now it just means has the same cardinality. Okay. So if A has the same cardinality as some j sub n for some n, we call a finite, obviously, right? If A has the same cardinality as the natural numbers, then we call it countable. We call A countable. Some people say countably infinite. Three, if A is finite or countable, then we call it at most countable. And 4, if A is not finite and not countable, then we call it uncountable. Call it uncountable. And what we'll see is that the real numbers are uncountable, right? And the rational numbers are actually countable. So let me make just one comment. For A to be countable, right? A countable means that there's a map. Which I'll call little a, going from n to a, that is 1-to-1 and onto. Right? That's what countable means, that your cardinality is the same thing. In other words, there's a 1-to-1 onto map from n onto a. Right? And what that means is that there's a sequence, i.e. there exists a sequence, a sub I equals 1 to infinity, where which is 1-to-1 and onto. Right? That you can turn A, roughly speaking, A can be made into a non-repeating sequence. So that's what countability means. Right. So for example, right, like if I think about the rational numbers that lie in 0, 1, right, I can make that into a sequence by considering the denominators. I'll say, like, let's consider the denominators of where the denominator is 1. Right? I have 0, I have 1. Right? Where the denominator is 2, well, I've got 0, 0 over 2, 1 over 2, and 2 over 2. Right? I've got 0 over 3, 1 over 3, 2 over 3, and 3 over 3. I don't include the ones that are repeating because I want to make a non-repeating sequence. And 4, I've got 1/4, 2/4 is already on there, 3/4 is not, and so on and so forth. Right? And so you see that going on in this way, I can create a sequence that hits every single rational number between 0, 0, and 1. Right? And so this gives me this gives me that the 1-to-1 map from here, from this sequence, this non-repeating sequence, gives the one-to-one onto map from n to q intersect 0, 1. Right, and so you see that the natural numbers, I'm sorry, the rational numbers in 0, 1 are a countable set. Okay. 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 So yeah, the first thing that we do in this chapter is countable sets, and the reason is that we're interested in infinite sets, right? We're going to be doing a lot with infinite sets. Sometimes those infinite sets are kind of complicated, but if we're lucky, we can find a countable set that lies inside that set that maybe is dense within it. And so, if we want to prove some result on the main set, sometimes it's enough to prove the result on a countable subset, a countable dense subset. Okay, so that's why we care about this. Yeah. Okay, so just a little bit more about well, a few more pages about countable sets. So theorem. Every infinite subset of a countable set is countable. Okay. Okay. Which is, as you might expect, right? That in other words, what it's saying is that you can't have an uncountable set sitting inside of a countable set, right? That's impossible. Okay. Okay, so can't have uncountable inside countable. Okay. So proof is pretty straightforward. You say, well, let E sit inside A, where this guy is infinite, and this guy is countable. Okay. A countable means that A can be that we can create a map, little a, going from n into A. Right, where this is one, there exists a map that is one-to-one and onto. So I'm just going to use my notation. One-to-one and onto. So there exists a one-to-one onto map from n into A. Okay, so which is basically the same thing as saying that A can be written as some sequence, A1, A2, A3, blah, where none repeat. Okay. So now, basically we want to create a sequence that will cover E. So, as you might expect, you say, well, let n sub 1 denote the first natural number. Such that A sub n1 is in E. Right? And then let n sub 2 denote the next natural number such that A sub n2 is in E, and so on and so forth. Right? Etc. Then, if we let E sub I be A sub n sub I, right, then that will be this non-repeating sequence covers all of E. Right? This covers all of E. And so you have, so is a one-to-one onto map from N onto E. Okay. Okay, is that clear enough? That makes sense to people? Any questions? Maybe, yeah, I'm going to go outside, talk to a neighbor for a minute, just to see if you can come up with a question if you have a question.
Kind of like a one-to-one like stuff kind of exists. I think I'm lost over here. And then sources are like natural. They take the natural steps to. It's interesting that it seems like obviously gaps.
Yeah, any questions? Anybody? Yes, Wyatt. Yeah.
I've heard that like rationals are also a countable set.
Yes.
So I'm wondering how we go about proving that.
Yes, I'm just about to do it. I'm just about to do it. So we've just shown that if you look at the rationals in 0, 1, that's countable, right? That was, and then certainly we can do that for any interval 1, 2, 2, 3, et cetera, et cetera. And so what the theorem that we're just about to prove is that a countable union of countable sets is still countable. Okay, and it's not too fancy. So let me prove that. So theorem. So let E sub n from n equals 1 to infinity be a sequence of countable sets. And this is how I always make countable. I always abbreviate it CTBLE. Let this be, suppose you have a sequence of countable sets, then their union, which I'll call S, is also countable. Okay. And the proof is basically to say, well, look, each E sub n is countable, so can be expressed as some sequence which I'll call xn1, xn2, xn3, and so on and so forth. Right. So the first index indicates what set you came from, and then 1, 2, 3, etc. indicates the position within the set. So okay. So then consider Yeah. So consider this sort of array of numbers, array of points. So x11, x12, x21, x22, x23, etc., x31, x32, x33, etc. Okay. And what we're going to do is we're going to go like this. We're going to create a new sequence in this way by kind of looping back and forth. Okay. So then so S can be arranged in a sequence, possibly with duplicates. Right, because some of these terms might be the same, but just toss out the duplicates. Right, so eliminate the duplicates. Eliminate the duplicates, and you get a map, a one-to-one onto map to the natural numbers. Okay, and you might worry that the only thing that you might have to worry about is that is this set actually infinite? But since E1 is contained in S and E1 is infinite, so we know that S is not finite. Okay, so you know that it's at most countable, and you know it's not finite, so it must be countable. Yeah.
I'm a bit confused what you mean when you say one-to-one onto map to the natural numbers. Does that mean the natural numbers are like our inputs?
Maybe you can say from the natural numbers. Would that be better?
Yeah, I'm so confused what exactly that means.
Oh yeah. So that was the sort of thing. Like, do you remember when we had the natural numbers, and then we created a map to the odd to the even numbers?
Mm-hmm.
Right. Right. So that map was one-to-one in the sense that no two natural numbers got mapped to the same number. So that was the one-to-oneness. And then the onto-ness meant that we do hit every single element there. Is that what you're asking?
Yeah.
Okay.
I got it.
Okay.
Thank you.
Okay, sure. Okay, so so that's why if you have a countable any countable set of any countable collection of countable sets is still countable. The union is still countable. Okay. Yeah. Okay. I think we have time for one more small result. So I was hoping to get to showing that R is uncountable. Actually, let me do that instead. Okay, that's more fun. So let's close with that. So R is uncountable. Okay, and this is a famous kind of argument called Cantor's diagonal process or diagonal argument. Okay, and the way we're going to do it is by looking at, so consider all sequences, and this is kind of out of order, but I'll fix it later. Consider all sequences of zeros and ones. Okay, so like 0, 0, 0, 1, 0, 0, blah, blah, blah. Okay. So all possible sequences of zeros and ones. Okay. And if you think about it, those correspond to those correspond to the real numbers in the interval 0, 1 via binary representation. Right? Every number in 0, 1, you can represent it as 0.01, 1, 0, as some sequence using binary representation instead of decimal representation. Okay. So our claim is that this set is uncountable. Okay. And the proof is kind of is really clever. What you do is you say, well, suppose it is countable. Suppose it's countable. Right? Then put them in order. Okay. So suppose you've got the first sequence, and I'm just gonna. So you've got all the sequences. You've got the first sequence. You've got the second sequence, et cetera, et cetera. Okay, so here are all the numbers, right? If they're countable, all the numbers between 0 and 1 are here, or all the sequences of 0s and 1s are here. Okay, so we'll now create a sequence not on the list, right? That will be a contradiction because supposedly we had the list of all numbers, right? So we'll create a sequence that's not on the list, and we'll do it by toggling everything down the diagonal. So you say, right, let me write it this way. If a number is, so let me say, define twiddle of a number to be 1 if x is 0, and 0 if x is 1. Okay, so it just flips the number. Okay, so now consider the sequence x11 twiddle, x22 twiddle, x33 twiddle, and forever. Okay. That sequence cannot be the first sequence because it disagrees with it at the first element. Right? Its first element is x11 twiddle. It's not this guy because this guy had a 1, that guy has a 0. It can't be the second sequence because it disagrees with it at the second position. It can't be the third, and so on and so forth. Right? This sequence disagrees with the nth sequence at the nth position. So is not any of the sequences listed. Contradiction. So that's Cantor's diagonal. In other words, Q is not Q does not have the same cardinality as R. Okay, sorry to keep you going.
So I'm not actually enrolled in this class.